All right, folks, I'm ready to get started. Welcome back, all of you, to the last day of the third week together. So 3 weeks down, 13 to go. We're getting somewhere. We're not anywhere too significant yet, but it's definitely building up. So I hope you are all taking both this class and your other classes very seriously at this point, getting things done. Please make sure that you are. If not, like, now is the moment. We have started to cover this chapter, which will finish on Monday, actually. So it's enough of a challenge, this model and sort of the math that ultimately reflects the model, that it requires, 3 different meetings to cover it in the way that I need to cover it, in the way that I hope will, at least to those of you that are truly interested in doing well in this class and interested in what we're doing, to have an opportunity to do well. Are there any questions about anything before I jump into the material? Great. So last time we started covering this model, the rational consumer choice model. Essentially, the model is a way for us to capture the consumption behavior of a representative consumer, just a person that is choosing to consume the things that they prefer the most, given that they have a limited amount of income, that those things have prices. So even though people in general want to consume as much as possible, we are restrained by the fact that we can't, because things have prices. Again, prices serve that rationing function of getting those things that people value to those that value it the most. And so essentially what this model is like the mechanics of that. Like, this is what happens behind the demand curve. And we'll actually use it in the next chapter to derive the demand curve. So super powerful model, but the intricacies are not necessarily intuitive unless you are really in tune with what the model is telling you. So that's what I've been building up. I've been building up the basic components, which are, one, the fact that there are prices and people have income to pay for things that have prices, and that is embodied in the budget constraint. And then the other is that people have preferences over things, and that is embodied in the preference ordering, which graphically looks like the indifference map that we covered last time. And so today we'll put them together and we'll get to the consumer equilibrium, in which the consumer is consuming as much as they can of the things they prefer the most, exhausting all of their income, because we do assume in this class that the hypothetical representative consumer is exhausting all of her income on what she's purchasing. And then, so we'll talk about that equilibrium, which is known as the best feasible bundle, most affordable bundle, different ways of characterizing it, but that's just the name of the section in the book. And then we will look at the same equilibrium via the utility function approach. So that will be sort of the bridge from the graphical stuff that gives us intuition about what this equilibrium means to the math. So injecting the utility stuff in there will then help us to be able to ultimately get to the mathematical problems that will reflect, again, everything that we're talking about, but just in mathematical terms. And unless you understand the model, you're not really going to understand what we're doing mathematically. So that it's all about building the intuition with the words and the graphs, and then securing the logic via the math. The math is always represents and captures like really tight logic, and also then allows us to think of the more complicated cases where there's an infinite amount of goods and people are choosing amongst those, and there's a consumption bundle that reflects what they prefer the most in a society, across all representative individuals, which then represents consumption for the society as a whole, which again can then be used to look at the behavior of any price aspect of the economy. If you try to project the price of anything in the economy and you're not considering what households are doing, then you're missing a major component of the economic forces that are affecting that price likely. And then as we move forward in the course, we'll be looking at the mechanics of what happens behind the supply curve, and that'll be more complicated because the supply decision is based on different costs, and different markets will have different structures, which will lead to different approaches by firms. So we have to consider each individual case. So that's a lot of what happens in this course past the first exam. It's all about kind of going through that, learning the mechanics of that, and then applying it to different cases to really understand what's happening behind the supply curve. And ultimately, what is happening is that producers are maximizing what they're producing, subject to the fact that they're constrained by their costs. So you'll see that in most models as well that have anything to do with trying to project prices. You'll see the production side of the economy being represented by a representative consumer who is maximizing their profits ultimately, subject to the fact that they have costs. And then on the consumption side, you have a representative household that is maximizing their utility, their satisfaction of what they're buying, what they're consuming, subject to their budget constraint. So again, these two important components are super important to any sort of model of the economy as a whole that's meant to focus on a price of an asset, a entire sector of the economy, an industry, whatever. And so you need to be able to understand what the model is telling us about these individual agents, and then ultimately, once you understand that, then you'll understand the relationship between those important components of those models to whatever ultimately they're forecasting. So a lot of what I just said is basically this whole class, and this part of the course highlights the consumption side, and so we'll be done with the representative consumer and the consumption problem by Tuesday, and then we'll jump into like kind of extensions and expansions of what we already learned. But this is like the heart of the consumption side, and so you need to spend some time like really understanding it, just at the very least to do well in this class, but ultimately to also kind of know how the household behavior is being accounted for in most economic models. Even if you think about video games that have like those virtual worlds with our economies within those, if you look at the coding, like you'll see like components of what we establish here in those as well. Like it's basically like standard. So it's important for you to have an understanding about it. And my job is to get you to get you to have that understanding, not just based on like the graphical depictions of the model, but also how that translates to the math. And so that's what I'm trying to do with these three meetings that cover this model. So again, I started by setting up the components. We're going to talk about equilibrium today, and then we'll establish this new perspective on the same equilibrium via looking at it as an overall function that's being constrained, and the function is the utility function, which I'll talk about. And then briefly, I'll start the first math review. You need to be able to do the problems that reflect the model, which involves managing exponents, and then we'll be done for the day. And then Tuesday, we'll cover a math review on how to do derivatives, and then we'll do a few of these problems, kind of putting it all together, and you'll see why I needed to kind of build it up as much as I do. And then on the end of Tuesday, I'll also establish this other approach to doing the problems, which is a little bit more advanced, which I'll consider extra credit on the exam. All right, so previously, again, we started setting up the main components of the model by highlighting the opportunity or the budget set, what folks can buy given the fact that they face prices and they have an income that constrains them. So any particular combination of two or more goods is a consumption bundle. So ultimately, whatever is chosen it will fall within that bundle. In the world that we're considering initially, there's only 2 goods in the world, so each consumption bundle is only made up of some of the first good, food, and some of the first good, shelter, some of the second good, food. But again, like in the more realistic, complicated cases that you would see in practice in models that use these components, you'll see an infinite amount of goods, and there's a way of dealing with an infinite amount of anything that requires a little bit more sophisticated math to be able to understand. But the heart of it is what you see here. Like the basic logic of it can be demonstrated to you in just a simple 2 good world. And then everything that we get from it, all the insights do translate into the more complicated case. All right, anyway, so consumers can buy bundles of goods. Bundles are just the combinations of the goods available. The goods they buy have prices. Consumers have a budget. So if we assumed in this case the consumer to have $100 in income, M represents income in this model, then this line represents the budget constraint. It represents the combination of all the bundles that the consumer can buy if the consumer exhausted all of her income. If she only bought food in this case, we know the price of food is $10, so $100 divided by 10, the most she could buy of food is 10 units. If she only bought shelter, the price of shelter is $5. 100 divided by 5 is 20. So that's what this consumption bundle represents. And then the in-between cases are all the other bundles that are embodied in this line, which again represent the bundles that she can afford and exhaust her income. Now, the slope of the budget constraint represents the relative price of the 2 goods, also known as the opportunity cost of the goods. So if we look at the slope, in this case, we found it to be -1/2. What that's telling us is that based on market prices, based on the fact that there are prices being set by markets that are beyond the control of the consumer, that in order to consume 1 unit of shelter, she has to give up 2 units of food. And you can measure the opportunity cost in this simple case of the other good as the reciprocal of that. So in order to get 1 more unit of food, she needs to give up half a unit of shelter. So just the reciprocal of 2. We also derive the fact that we can get the slope of our budget constraint, which again captures and reflects this relative price of the 2 goods, by taking the ratio of the y-intercept, which represents the most of food she can buy, which is income divided by the price of food, divided by the most shelter she can buy, which is represented by the x-intercept. So M divided by the price of shelter. We've got a ratio divided by a ratio, which is equal to a ratio times the reciprocal of the bottom ratio. So you have M over the price of food times the price of shelter over M. The incomes cancel out, and thus we're left with this expression here, which is another way to characterize the slope of our budget constraint as negative the ratio of the price of good S to the price of good F. So the price of the good on the x-axis to the price of the good on the y-axis. So that's another way of representing our slope that has meaning within the model. And you'll see why it's relevant when we get to the equilibrium in a second. So the line, again, constraints are affordable set, the consumption bundles that can be afforded. Any consumption bundle that is not on the line is feasible. It's able to be purchased, but it does not exhaust all of the income. And then any points beyond the line represent consumption bundles that are beyond the income of the consumer. We could represent the budget constraint by starting out with this equality between income and the value of everything that's purchased. So the income of the consumer equals the value of all the shelter, the price times the quantity sold, plus the value of all the food, the price times the quantity sold. And then we had food on the y-axis, so we can use this to get to a slope-intercept form for the line, which also has a lot of the information we had just derived from looking at it graphically. So the most that the individual can buy of food, if she only bought food, is the y-intercept for the line, which is the budget constraint. And then the slope of the budget constraint can be represented as a negative ratio of the price of shelter to the price of food, or also just the price of the good on the x-axis to the price of the good on the y-axis. All right, and we talked about shifts of the budget line. So two things that could affect the budget line or budget constraint, however you want to call it, are changing prices and changing income. So if the price of a good changes, let's say the price of shelter goes up, that means that the consumer can buy less shelter now if she only bought shelter. So that would bring in the horizontal intercept, which would rotate the line in. Same thing would happen if the price of food went up. The vertical intercept would pivot in as well. If the price of something goes down, so if the price of shelter were to go down, we were over here, then the consumer can buy more, so it would rotate outwards. If the entire income changes, then prices aren't changing, and graphically it can be represented as a shift of the entire budget constraint. So if the income goes down, you shift the line in. If the income goes up, you shift the line out. We see that when incomes change, the relative price of the goods don't change, and so the slope stays the same, and that's why you have a parallel shift. Versus if a price does change, then the relative price of the goods changes. The exchange rate of one good for another in the market does change. In this case, because the good has become more expensive, and now shelter has become more expensive, that means that the slope is now going to be bigger. That means that to get one more unit of shelter, you need a lot more food to exchange for it. The opportunity cost of it has gone up. So those are the mechanics of price and income changes and how they affect the budget line. And again, you can represent a world with more than two goods graphically in the simple case by saying that there's one good that's called the composite good that basically embodies all money left over after the consumer has spent their money on a specific good that's being considered. So generally the composite good will be put on the y-axis, and by convention, by assumption, we assume the price of the composite good is $1. Then we established the other main component of the model, which was consumer preferences. So how do we establish like the preferences of somebody? Well, we set up what's called a preference ordering. The preference ordering has four properties. One is completeness, meaning that for each consumption bundle, the consumer can either say that one is better than the other. If you have A and B, let's say two consumption bundles, the consumer can either say A is preferred to B, or B is preferred to A, or they are equally attractive. So one of those three statements must be able to be made about two consumption bundles, and thus they can be ranked. So completeness is the first property, more is better is the other. The consumer, we assume, prefers more than less of anything. Transitivity was the third property we assume for the preference ordering, basically saying that if you have, let's say, one good that's preferred to the other, and the other is preferred to the third, and the first is preferred to the third. Also, that can be used to say if one is equally attractive as B, let's say A is equally attractive as B, and B is equally attractive as C, then A will also be equally attractive as C. And also, if A is preferred to B and B is equally attractive as C, then A will be preferred to C, transitivity. And then finally, the fourth property, convexity. Convexity basically says that the consumers don't prefer the extreme cases of just one or the other, of either consuming all of one good or the other. They prefer a mix of the two. And then we can use these properties of this preference ordering to then represent those preferences graphically via indifference curves and an indifference map. So an indifference curve, so again, if you have the two goods, in this case food and shelter again, an indifference curve is a set of bundles among which the consumer is indifferent. So along an indifference curve, you can have a combination of food and shelter up here that has a lot of food and a little bit of shelter, and then a combination of food and shelter down here that has a little bit of food and a lot of shelter, and the consumer will be indifferent between the two, meaning that they are equally preferred by the consumer. And there are indifference curves everywhere, which embody the indifference map, which again reflect the preference ordering graphically. Indifference curves closer to the origin represent bundles that are less preferred to bundles that are on indifference curves further away from the origin. So there's increasing satisfaction as we move away from the origin. But again, along any indifference curve, any two bundles along it, a person equally prefers those. So along this one, this bundle up here is equally preferred to this bundle here. But any bundle on I4 is preferred to any bundle on I3 because they provide more satisfaction. And these curves have four properties. One, they are ubiquitous, they are everywhere. Two, indifference curves are downward sloping. If they are upward sloping, then it violates the more is better assumption. Indifference curves from the same indifference map cannot cross. If they do cross, then the logic of the preferences breaks down. And indifference curves become less steep as we move from left to right along them, meaning that they are convex, meaning that they are capturing that quality that, again, says that consumers prefer mixtures of the two goods versus the extreme cases of just one or the other good. All right, so that's what we did last time. Now let's move forward. Let's talk about equilibrium in this model. All right, we can now determine how the consumer should allocate her income between two goods. So there's going to be a way for her to use her income in the way that's going to make her the happiest. And therefore, she should choose that, given what we've established about the nature of her preferences and the budget constraint. So the bundle that she prefers will be the best affordable bundle, the most preferred bundle of those that are affordable. So again, they will fall within the feasible set, the affordable set. So consider again the choice between food and shelter that confronts a consumer with an income of $100 and the price of food to be $10 and the price of shelter to be $5. The more is better assumption implies that the best affordable bundle must lie on the budget constraint, not inside of it. So let's say you have, the best affordable bundle cannot lie in an indifference curve that lies partly inside the budget constraint. So let's say you have this bundle here, bundle A, on this indifference curve, which lies within the budget constraint. So obviously, this bundle is feasible. It can be afforded. It falls within the affordable set. But certainly, given what we know about indifference curves and that they are ubiquitous, we know that there are indifference curves that have consumption bundles that will give a greater level of satisfaction to this consumer. So therefore, if an indifference curve lies within the budget set, as this one does, then that will not yield the best, most preferred affordable bundle. All right. Since it must lie on the budget constraint itself in order to exhaust the income of the consumer, which we know it has to lie on an indifference curve that intersects the budget constraint only once. So let's say we have another indifference curve a little bit higher. We know that all of these consumption bundles are preferred to all of these consumption bundles. The consumer would want to consume B out of those because B lies on the budget set, on the budget constraint, which means that the consumer's entire income is being exhausted on that consumption bundle. And so this one is definitely preferred to A. But in this case, we also have another one over here that does the same thing. And they are equally preferred, right? The consumer is indifferent between those two bundles on this indifference curve. And also we know that there are more indifference curves and that this consumer can do better than this. So here we have another indifference curve, and this one happens to be touching our budget constraint just once, which is what we are looking for. So that is going to represent the indifference curve that is going to have the best affordable bundle. The bundle that the consumer prefers the most and exhausts all of her income. So it's the bundle that it's on the highest indifference curve. It's the one that she can afford because it is on her budget constraint and prefers the most possible. any bundle on a higher indifference curve that would be preferred to this one will not be affordable, will not fall within the affordable set. And so this is the best affordable bundle. It represents the, again, combination of goods and services that will make this consumer the happiest and exhaust all of her income. So the marginal rate of substitution, which is the slope of the indifference curve, at point C is going to be exactly equal to the slope of the budget constraint. So at the most affordable bundle, our marginal rate of substitution is equal to the slope of the budget constraint, which is equal to the price of the good on the x-axis to the price of the good on the y-axis. The slope of the budget constraint represents the opportunity cost of shelter in terms of food, as we know, while the slope of the indifference curve represents the benefit of consuming shelter as compared with consuming food. So remember, the indifference curve represents preferences, and thus the slope of the indifference curve represents like the subjective trade-off that the consumer has to make in terms of what she prefers when she's either increasing or decreasing how much she's consuming of one good versus another. The slope of the budget constraint is the trade-off she has to make, that she's being forced to make by the market. So there's two trade-offs that are meeting, and at this point they are equivalent. So at that point the trade-offs are equivalent, and it's the best that she can possibly do. Since the slope of the budget constraint is 1/2, the tangency condition tells us that half a pound of food would be required to compensate for the benefit given up from the loss of 1 square yard of shelter. So just in terms of the budget constraint, the 1/2 tells us that 1 unit of shelter has an opportunity cost of half a unit of food. At point C, the subjective trade-off is also the same. At point C, the consumer views an additional unit of shelter to benefit her in terms of half a unit of food. Like that's sort of like the benefit that she gains from consuming an additional unit of shelter along her indifference curve. And so the extra benefit from consuming an additional unit of shelter is equivalent to the extra cost having to be incurred by consuming an extra unit of shelter at that equilibrium. If the consumer were at some other bundle on the budget line for which the two slopes are not the same, then it would always be possible for him or her to purchase a better bundle. So let's say we were at point B. So at point B, we see that the slope of the indifference curve in absolute value is less than the slope of the budget constraint. So therefore, the extra benefit she gains from consuming 1 more unit of shelter is less than the cost she has to incur to consume 1 more unit of shelter, which means that she's going to want to consume less shelter until they are equivalent. So at B, the marginal rate of substitution, which is again the slope of the indifference curve, is less than the relative price or the market rate of substitution, or just the slope of the budget constraint, however you want to call it. There's different names for things. If we were at point D, at that consumption bundle, then we see that the slope of the indifference curve here is greater than the slope of the budget constraint, which means that the extra benefit she gains from consuming 1 more unit of shelter outweighs the cost of consuming 1 more unit of shelter. So that means she's going to consume more shelter and less food, and that will get her to C. So on both sides of the equilibrium, if she's not at the equilibrium, just the very nature of this interaction between her own subjective trade-off and the trade-off she's facing based on what the economy is making her trade-off, will get her to the point where they are equivalent and she is as happy as she possibly can be.
Does that always work out mathematically though? Like what if that point is like a happy unit?
It won't. It'll get back to that equivalency point mathematically. In fact, we'll talk more about how that makes more sense mathematically when I inject the utility dimension into this. So that is our best affordable bundle. This is like the basic intuition of what it means for a consumer, a rational consumer. And when we say rational in economics, we're talking about agents, decision makers that are always choosing the option that makes them best off. And so this rational consumer is going to choose this bundle because that's the bundle that makes her best off. It's the equilibrium for the rational consumer choice model. There are, of course, going to be some exceptions depending on if you have some extreme cases. So in this case, so if you remember last time I talked about how like the curvature of the indifference curve reflects different preferences. So that's how you can capture different sort of attitudes towards whatever goods are being offered in a market. In this case, we have super flat indifference curves, which means that this consumer doesn't value shelter very much at all. The marginal rate of substitution is pretty flat all along it. That is under this situation where you have these pretty flat indifference curves, then that's going to lead us to a corner solution. In a choice between two goods, it's going to be a case in which the consumer does not consume one of the goods. So in this case, she will prefer to only consume food because of the nature of her preferences, which are embodied in these relatively flat indifference curves. In these cases, there may simply be no point of tangency. The marginal rate of substitution may be everywhere greater or less than the slope of the budget constraint. In this case, it's less. So the added benefit of consuming an extra unit of shelter is always going to be less than the cost of an additional unit of shelter. And therefore, it's never going to be worth it for this consumer to consume any shelter, and she will choose to just consume food. So at A, the marginal rate of substitution is less than the absolute value of the slope of the budget constraint. Even though this consumer does regard shelter with some desirability, the best she can do is to spend all her income on food. But you always have to talk about the exceptions whenever you're doing anything like that involves like very finite rules. But in the end, like it is going to be an extreme case. You're not often going to see this, but it needs to be acknowledged that that can happen. So she would have to give up too much of food to make the purchase of even a single unit of shelter worthwhile, given the nature of her preferences embodied in those very flat indifference curves, which can be specified by the modeler. So you can say, well, I'm modeling an economy, and like the consumers in this particular markets that I'm interested in have, you know, this kind of preference, right? It's not your standard type of preference. They have like very flat preferences, meaning they mainly prefer the one good. So then you would have an equation that would capture that sort of flat marginal rate of substitution to be able to then differentiate it from consumers that have like more normal preferences. Yeah.
Can you go back to that?
Yeah.
You may have already answered this, but how do you know of those three which you would choose because they cross line one?
So remember, as we get further away from the origin, they represent higher levels of satisfaction. Yeah. So she wants to consume at the highest indifference curve possible, right? All right, so indifference curves that are not strongly convex, like the one we saw, are characteristics of goods that are easily substituted for one another. Corner solutions are more likely to occur for such goods that are almost certain to occur when goods are perfect substitutes. So when they are perfect substitutes, you're going to have straight lines for the indifference curves. And whenever that happens, you are always going to have a corner solution. In this case, the corner solution is going to be this one here. So for such goods, the marginal rate of substitution does not diminish at all. It is constant. If the indifference curves happen to be steeper than the budget constraint, we get a corner solution on the horizontal axis, as we see here. And if the indifference curves are less steep, we get a corner solution on the vertical axis, as we saw on that other one. Yeah. So we're just talking about preferences. We're not talking about elasticity of demand in general. We'll talk about that in a later chapter, but like we're just talking about preferences. So in this case, what this is telling us is that there's no diminishing marginal rate of substitution, meaning that the consumer doesn't prefer like less of a good as they consume more of it. Like the amount they want any good at any time is going to be constant. And it's going to be constant across both goods, and thus the slope of their indifference curve, which represents how the rate at which they're willing to trade off one good or another, will not change. And so you'll have those straight lines to embody that. All right, so indifference curves when there are more than two goods, again, you can use the composite good approach. When there's more than two goods, we can construct indifference curves by using the same device we used earlier to represent the multi-good budget constraint using the composite good. So again, the composite good is the amount of income the consumer has left over after buying the good X. All right, now let's add an extra dimension to this whole thing, which will help us to understand the equilibrium a little better, which will bridge us to the math. So in this section, we expand the understanding of the indifference curve map and the consumer choice problem. We introduce the concept of utility, a concept you were likely introduced to in your introductory micro courses. So the utility of a consumer is a measure of the satisfaction the consumer derives from consumption of goods and services. So that thing I've been talking about, that satisfaction, that happiness that consumers gain from consuming, we call it utility. And essentially, it's a ranking system. The number itself doesn't have any inherent meaning. It only has meaning relative to the other numbers. A unit of utility is called a util. So you can have the utility of an individual with respect to one good. And that's one case of a utility function. So an individual's utility function gives the total utility generated by his or her consumption bundle. So if there's only one good in the world, then the consumption bundle is only made up of the one good. And her utility function can be easily plotted, as you see here, where you have, let's say, total utility on the y-axis and the quantity of the good being consumed on the x-axis. And then the slope of that line, that curve, is going to tell us how much extra utility she gets from consuming an additional unit, what we call the marginal utility. So here is this person, Casey, her utility function. We're talking about how much utility she gets relative to how many clams she eats. So she's been waiting all week for that clam, all you can eat buffet, and finally she eats that first clam, and it is delicious. She loves it. She gets a lot of satisfaction from it. She gets a lot of utility from it. So going from 0 to that first one, she has a marginal utility of 15 units, which is plotted down here. This plots her marginal utility. She's finally had that first clam, not satisfied, definitely going to go for more clams. Eats the second clam. Second clam makes her very satisfied, but not quite as satisfied as that first one. So the marginal utility, that extra utility gain from consuming that second clam, was 13 utils. So her marginal utility diminished, which we can see by the fact that this line is decreasing. This is plotting her marginal utility. So her marginal utility is diminishing, which means that the utility curve is flattening out as we move to left to right, and that is what captures the fact that marginal utility is diminishing. So going from the 6th to the 7th clam, she's eaten 6 clams, she's pretty happy. 7th clam still makes her happy. So her utility is positive, but her marginal utility has diminished quite a bit to just 3 units, which we see plotted right here. So again, the marginal utility of a good or service is the change in total utility generated by consuming one additional unit of that good or service. It is also the slope of the utility function. According to the principle of diminishing marginal utility, each successive unit of a good or service consumed adds less to total utility than the previous unit. So that's generally what we assume about most consumption behavior, is that it exhibits diminishing marginal utility. In that case, we just saw perfect substitutes where the preferences were straight lines. We didn't have that. And so we have to be explicit about that if we're going to consider that case. The utility of consumption bundles with more than one good behaves similarly. So again, we're talking about a world where there's only one good, clams. Her consumption bundle is made up of just clams, right? Let's say we added another good in there. That means her utility would be a function of 2 variables, 2 goods. So that would be a 3-variable relationship, which would have to be represented 3-dimensionally. Suppose, for example, that Tom consumes only food and shelter, and that his utility function is given by this expression here, where utility is a function of both food and shelter, whereas before, I think Kelly, or whatever her name was, her utility was a function of just clams, right? So it would be U of C. But Tom's utility is a function of food and shelter. So his utility is a function of both of these, and it takes the functional form F times S. So it takes the form of a product of the two goods. F denotes the number of pounds of food on a particular day. S denotes the number of square yards of shelter during a particular week, whatever it was. And U is utility. So if he consumes 4 units of food in his consumption bundle and 3 units of shelter, if we plug those in, then we know that Tom gets 12 utils from that consumption bundle made up of food and shelter. So the utility function is analogous to an indifference map in that both provide a complete description of the consumer's preferences. In the indifference curve framework, we can rank any two bundles by seeing which one lies on a higher indifference curve. In the utility function framework, we can compare any two bundles by seeing which one yields a greater number of utils. And it is straightforward to use the utility function to construct an indifference map. So now I reveal to you that an indifference map is actually what are called traces of a three-dimensional utility function. So in the language of utility functions, an indifference curve is all combinations of F and S that yield the same level of utility. The indifference curve that corresponds to 1 unit of utility represents the combinations of all consumption bundles that yield 1 util. So all these bundles, in this case, yield 1 util along this indifference curve. We know that utility is a function of food and shelter and takes this functional form. So if we set our utility equal to 1, then we can solve for the equation of this indifference curve by solving for F in terms of S. I just switch the sides here, divide both sides by S, and that gets me to the equation for my indifference curve to be F equals 1 over S, which is the equation for that indifference curve. So an indifference curve basically just holds utility constant and then relates the two goods in a way that demonstrates a trade-off between the two. If the indifference curve represented a level of utility that was higher than this, let's say it represented consumption bundles that all yielded 2 utils of utility, then the indifference curve equation, we would set utility equal to 2, do the same math here, and then we would get to this equation for the next higher up indifference curve, corresponding to a constant level of utility across all consumption bundles of 2 utils. And so on and so forth. As we move away from the origin, we are getting to higher and higher indifference curves that correspond to higher and higher levels of utility. So again, the indifference curve map can now be revealed to be a series of traces of the edges of the flattened out slices of the three-dimensional utility function, where utility is a function of 2 goods. So this is a terrible representation of it, but it is kind of like, ultimately what it looks like is like a bowl shape. That's what it makes. It makes a bowl shape, like a round circular kind of dome shape. And on so this is just like a quarter of that dome. So you've got the flat part of the dome, the bottom of it, which is represented by the X and Y axis, and then you've got the height of the dome, which is represented by the Z axis. Utility is measured along the Z axis, which is the height of the dome. And so if you slice the dome at some level, that represents a slice at a level of utility. So if you slice the dome at this level here, at the height of 20 utils, and then you flatten it, you get a trace of the edge of the utility function, which we call the indifference curve, corresponding to a level of utility, in this case of 20 utils for each consumption bundle along it. If you were to go higher up that dome, slice it again, you would get this trace of the edge, this rounded trace of the rounded edge, flatten it down, and you would get the higher, next higher indifference curve that we see here, corresponding to a level of utility of 30 utils for all consumption bundles along it. And so that's what indifference curves really are. They're just part of this three-dimensional construct that results from a utility function that's a function of two goods. So if we place, again, utility on the z-axis in a three-dimensional space and slice the bowl-shaped utility function at each positive integer, then flatten those slices into a two-dimensional plane, we get the indifference map. In the indifference curve framework, the best attainable bundle is the bundle on the budget constraint that lies on the highest indifference curve. Analogously, the best attainable bundle in the utility function framework is the bundle on the budget constraint that provides the highest level of utility. All right, so at the optimal bundle, the slope of the indifference curve, or also known as the marginal rate of substitution, right, equals the slope of the budget constraint, as we know. So suppose food and shelter, again, have those prices of PF and PS. If we let the change in F with respect to the change in S denote the slope of the highest attainable indifference curve, so this indifference curve here that corresponds to utility level of 3 utils. And so this is the slope of the MRS at the optimal consumption bundle. Then the tangency condition, when we talk about tangency in math, we're talking about like just touching, right? Like, so the condition of these two just touching says that the slope of the indifference curve is going to equal the slope of the budget line at that optimal bundle, as we established earlier. So therefore, the marginal rate of substitution is equal to the slope of the budget line, which we know to be equal to the ratio of the price of the good on the x-axis to the price of the good on the f-axis. On the y-axis. So to find out the analogous condition in the utility function framework, we must use the concept of marginal utility that I talked about earlier. All right, so now we're going to look at how utility factors into the marginal rate of substitution and how that can then get us to an intuitive understanding of that equilibrium. So we'll let the marginal utility of good x be equal to MUX, and we'll let the marginal utility of good y equal MUY. All right, so here is an indifference curve. Let's say that a consumer is consuming this bundle up here with this much of good y and this much of good x, and she wants to consume this bundle over here, which will make her as happy as before because she is consuming along the same indifference curve. So to move from here to here, she is going to give up some y and gain some x. So if we represent the change in the consumption of good x as the change triangle of qx, that means that this change in the amount of x that's being consumed, in this case, she's increasing the amount of x. If we value that in total utility, it's going to be equal to that change in x times the marginal utility of x. As we move from left to right, we're giving up some y, so there's going to be a change in the amount of y that's being consumed, so we represent that by change in qy. And of course, that carries some utility with it, some marginal utility. It's being lost in this case because she's consuming less of y. So the change in total utility resulting from losing some y is going to equal the amount of y that's lost times the marginal utility that it carries, the value in satisfaction and utility that losing that amount of y carries. So along the indifference curve, we know that the total utility has to remain the same, that it is constant. So therefore, as we're gaining some utility, that has to be equivalent to the amount we're losing. So if we now solve for our standard slope expression of a curve, which is the change in y over the change in x, we can divide both sides of this by the change in qx, and then isolate our change in qy by dividing both sides by the marginal utility of y. So I divide both sides by that to get that on the right-hand side, and then I'm going to divide both sides by the change in qx to get that on the left-hand side to get me to my standard slope expression, the change in qy over the change in qx in this case. And what that tells us is that the marginal rate of substitution of an indifference curve, the slope of the indifference curve can be represented as the ratio of the marginal utility of the good on the x-axis to the marginal utility of the good on the y-axis. Which is our marginal rate of substitution. All right, so the left-hand side is an approximation to the slope of the indifference curve. It's the rate at which the consumer is willing to trade x in terms of y. The right-hand side is the ratio of the marginal utility of good x to the marginal utility of good y. Quick practice problem just to highlight the logic of the marginal rate of substitution so you're able to understand what it means. So let's say we're dealing in a world where there are only DVDs and CDs, things that if you are interested can go to the Natural History Museum and find out about these things. They used to be used by people to enjoy entertainment. So let's say the marginal rate of substitution between DVDs and CDs is equal to 2. So the marginal utility of DVDs over the marginal utility of CDs equals 2. What does this mean as far as like the consumer? Like what is the subjective trade-off they're willing to make at whatever point they're at in terms of DVDs and CDs? So that's what you think it would be, given like what you normally would think of a slope. But remember, we derived this expression and we flip them, right? So therefore, what is this actually telling us? Exactly. You got to think of it the opposite way. So just make sure you're able to do that. Make sure you're able to understand what the marginal rate of substitution is telling us when we have some numerical value. So again, it means that the consumer is willing to give up 2 CDs for 1 DVD at their current allocation of CDs and DVDs. When is it valid? This relation may no longer hold at a different allocation of CDs and DVDs because we know that marginal rate of substitution is diminishing, changing as we are moving from left to right along an indifference curve. All right, so now going back to our example, we'll let the marginal utility of food be denoted by MUF. It denotes the number of additional utils we get for each additional unit of food. We'll let MUS denote the number of additional utils we get for each additional unit of shelter. As we know, at the optimal consumption bundle, the slope of the indifference curve is equal to the slope of the budget line. We know that the slope of our indifference curve, our marginal rate of substitution, can be expressed as the negative ratio of the marginal utility of S to the marginal utility of F. So I often leave out the negatives because once we look at equilibrium, since they're both negative, they both drop out and they're no longer there. And plus, we're always talking about a trade-off, and a trade-off always involves giving something up for something else. So they both necessarily are negative. So that's why I always kind of leave them out. So just be comfortable with that because you should always kind of know that the slope of budget constraints and indifference curves will always be negative. So the slope of the indifference curve, the marginal rate of substitution, is equal to the negative ratio of the marginal utility of the good on the x-axis, which is shelter, to the marginal utility of the good on the y-axis, which is food. Therefore, at the optimal consumption bundle, we know that these expressions must be equivalent. Because we know that these curves are tangent at that point. They're tangent at a point where their slopes are equivalent. So rearranging that expression, if we were to multiply both sides by the marginal utility of F to get that on the right, and then divide both sides by the price of S to get that on the left-hand side, we're going to wind up with this expression here. So what this is telling us is that at the optimal consumption bundle, the marginal utility per dollar spent by the consumer has to be equivalent. Every dollar the consumer spends on goods at this optimal point has to make her as happy across all goods. If not, then she would want to move away from that consumption bundle, consume less of the good that each dollar gets her less in marginal utility to the one that gives her more marginal utility. So this condition now has this intuitive interpretation that at the optimal consumption bundle, the ratio of marginal utility per dollar spent on all goods must be equal. Suppose we were at consumption bundle A. So at consumption bundle A, we see that the marginal rate of substitution is bigger than the slope of the budget constraint. So that means that our expression here is greater than this expression, right? Marginal rate of substitution is greater than the market rate of substitution, which is another way of talking about the slope of the budget line. Again, if we move this stuff around, then we see that the marginal utility per dollar spent on shelter is greater than the marginal utility per dollar spent on food at this consumption bundle. So spending $1 on shelter makes her happier per dollar spent than spending $1 on food. So therefore, it makes sense to spend more money on shelter and less money on food, right? So that gets her away from this consumption bundle. She's still going to consume along her budget constraint because those are the bundles that she can afford. But she wants to get to the one that's going to make her the happiest, so she's going to go to this consumption bundle here. If she's over here, then you're going to get the opposite case, where the marginal utility per dollar spent on food will be greater than the marginal utility per dollar spent on shelter, and therefore she's going to want to spend her money more on food than shelter because it makes her happier. And so she's going to go away from here to here, and then she's going to be happy. Now, the reason why they eventually become equivalent is because of diminishing marginal utility, right? As you consume more of a good, then each additional unit gives you less marginal utility than the prior unit, right? So even though over here the marginal utility per dollar spent is greater on food than on shelter, as she consumes more food and less shelter, the marginal utility starts to diminish for food, and then it starts to increase for shelter, and therefore eventually they equilibrate and she gets to that equilibrium point. So this means the consumer is willing to give up more food to get an additional unit of shelter that markets require if she's over here. This prompts the consumer to consume more shelter and less food. As this occurs, blah, 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 it gets her to that optimal bundle. That's what I said. All right, anyway, so that is our rational consumer choice model. That is what it means to have equilibrium in that model. That is how we relate it to utility. And then next week, we're going to do some problems. We're not done yet, by the way. I'm still going to cover exponents in a second. But next week, we're going to do some problems that basically establish a consumer that has a certain utility function. So you're given an equation, and you're told she has a certain amount of income. These are the prices she has to face in the market. And then the question is, how much of each should she consume? And the only way you can figure that out is to maximize the utility subject to the budget constraint. How do you maximize any curve? You take the derivative, you set equal to 0 to find the maximum. So you need derivatives in order to do that. So that'll get us to the solution of those problems, which will always be the optimal consumption bundle that we understand now very thoroughly, graphically, as well as how it relates to utility. So this is all meant to just give you intuition about what's happening in the problem so that you're not just doing a bunch of math for no reason and you're just memorizing some rules to get through a problem. No, you understand there's a logic to the overall model. The problem is just meant to solidify that logic, give you an example of how that logic is seamless within the problem, and ultimately provide you the insights you need to be able to carry forth your understanding of this model into more complicated applications. If you're in economics, you will definitely see more complicated applications going further into the 400 level classes. But if you're not in economics, then at the very least you understand that this is happening in those models that you're going to use in finance or maybe in some other systems that involve like some component of the economy interacting with other variables. So it's powerful if you think of it just in it of its own without context. It's pretty dry, right? But if you can appreciate economics for what it is and what this model is trying to do, then you might wind up liking it. Anyway, I'm just trying to make you interested as much as possible. I hope somewhere in there you can make this work for yourselves. But you have to just acknowledge that this exists and people use it. So it's better to understand it than not to understand it. All right, let's do a quick review of managing exponents when solving for a variable, because we're going to need to use this method to solve some of the problems. And I just want to make sure people are on the same page. There might be some people that are rusty on doing some of this stuff, and that's why it needs to be covered. And that's that. All right, so just quick properties of exponents. So let's say you have some number, some base b being raised to some exponent x, and that's being multiplied by the same number raised to some exponent y, and that is equivalent to that number b, that base, whatever it is, raised to the sum of those two exponents. If you have some number b being raised to some power x, divided by that same power number b being raised to some power y, then that is equivalent to that number b being raised to the difference between the numerator's exponent and the denominator's exponent. Properties of exponents. All right, you have some number b being raised to some power x, and then you're raising that whole thing to some other power y. That is equivalent to raising that power b to the product of those two exponents, x and y. So this is the situation in which you multiply the exponents versus this is a situation where you add the exponents. Let's say you have a product of two numbers, b and c, being raised to some power x. That is equivalent to the first number b being raised to the power of x being multiplied by the second number c being raised to the same power x. If you have some quotient b divided by c, some ratio, and that whole thing is being raised to the power of x, that is equivalent to the numerator being raised to the power of x divided by the denominator being raised to the power of x. Any number raised to the power 1 is equal to the same number. Any number raised to the power of 0 is equal to 1. Any number raised to some negative exponent is equivalent to 1 over that number raised to the positive exponent. All right, if you're a little bit rusty on these things, my best suggestion is for you to just like do a quick search of like properties of exponents problems, and you'll like find a bunch of problem sets that people post online. Sit down for half an hour and just do a bunch of them really fast, and just get it down again so that you have it once again, so that it's in your arsenal of things that you apply when you see that you have to, manipulate a problem to get to a solution by using the properties of exponents. Because this is something that will get you to the next step of what you need to eventually get to in solving a variety of complicated problems, including the ones that we'll be doing in class. Now, let's say you've got this expression here, and you're trying to solve for s, right? So now the only way you can solve for s is by employing your properties of exponents knowledge to try to isolate s. So we've got this term here being multiplied by this term here. They're not the same term, so we can't just like add the exponents, right? Same thing over here, and this is being multiplied by -9. But we do have similar terms in each of the two big terms that are being added, right? So we can use these terms to simplify them to some form where the exponent drops out, and then we can use these terms, these two terms here, to do the same thing. The exponents on each of them. So on this first term and this term here, you can get those to add to 1, and then the same for this big term here. So what I did was I focused on this simple term first. If you divide both sides by this term, 0.2 s raised to the -0.8 power, obviously it cancels out here, and then over here you obviously have 0.8 divided by 0.2. But you also have s raised to the power of 0.2 over s raised to the power of -0.8, right? So you have some number s, that same base, being raised to some exponent on the numerator over that same number on the denominator being raised to some other exponent, which means you have that number s being raised to the power of 0.2 minus the exponent of the same term in the denominator, which is minus -0.8. 0.2 minus -0.8 is equal to 1, right? So that gets rid of that one. And then, of course, you're dividing the whole thing by this term. So 0 divided by 2, obviously that's going to be 0 there. So that drops out here. So yeah, that drops out. over here, we're going to have 0.8 divided by 0.2, which is equal to 4. And then you've got s raised to the power of 0.2 minus negative 0.8. That's its power, which then will get us to 4s raised to the power of 1 there. So over here, what I did was I canceled out the 0.2s, and then I had s raised to the power of negative 0.8 minus negative 0.8, using, again, the properties of exponents. So you wind up with negative 0.8 plus 0.8, which is s raised to the power of 0, which is equal to 1, so it drops out. So that one's going to drop out, and then we're just left with this term here. That's the only change I did. I did this change 1 there, and then s raised to the power of 1 obviously is s. All right, so now we've gotten rid of that. Now we still need to get this other s out of the parentheses. It's the same term, but again, it's being raised to different powers, and they're being added here, so you can't do anything as far as combining them, but you can divide the whole thing, in this case, by 500 minus 9s raised to the power of negative 0.2. So dividing the whole thing by that term, once again, we're going to have this term here raised to the power of 0.8 minus negative 0.2. So that's going to be 0.8 plus 0.2, which is 1. So 500 minus 9s raised to the power of 1 there. And then you've got 4s times this term raised to the power of negative 0.2 minus negative 0.2. So that's going to equal this term raised to the power of 0, which is anything raised to the power of 0 is equal to 1. So that's going to drop out. So we're going to be left with this term raised to the power of 1. That's going to equal 1. So you got 500 minus 9s plus 4s times negative 9. So that's what we have there. And now we've gotten our s's out, and now we can combine our s's, and we can solve for s. So there's that same expression. We can combine these terms. That's going to get us to 500 minus 9s. I'm gonna combine these terms first. Minus 36s, and then we combine these. 500 minus 45s, and then get 500 on the right side, subtracting 500 from both sides. Or actually, I got this one on the right side. I added that to both sides. Divide both sides by 45, and then you solve for s. So it's a long process, and in order to solve for it, you needed to know all the properties of exponents. If you didn't exactly track it, hey, it was recorded. Go back, do the problem again. Look at exactly what I did on each step. Make sure that you understand what was done given the properties of exponents. You're not just memorizing a bunch of stuff, because that's not going to get you anywhere, memorizing exactly what I've done. You have to understand how to do the math so that then you can just do it on the fly, given different problems that you might be given. Again, I know some of you people already have this down, and that's great, but I am trying to help people that maybe haven't seen this in a while, haven't taken this in a while. I hope everybody can just be patient with that. But ultimately, you will get to a complicated understanding about how to do these problems, regardless of whether you start at a high level of understanding or a low level of understanding. Yeah. So where? Over here? Oh yeah, I just divided the, it was 0.8 divided by 0.2. And then that got me to 4. And then I had s raised to the power of 0.2 raised to, so again, you've got that same term there, right? S. They've got these exponents. So this is equivalent to s raised to the power of 0.2 minus negative 0.8, just based on properties of exponents. Do you see that? So that's going to equal 4s raised to the power of 1. So that's going to equal 4s. Do you see it? Okay. So you just have to be very careful. And even those of you that are good at this stuff, you see that you might wind up with an expression like this you need to solve for. You're rushing, you're confident, you make mistakes, you get the wrong answer. Be careful. Do every step. Again, economics is a difficult field because it's not just the economic intuition. It's not just the models and understanding the equilibriums and what they mean and all that, but it's also using the math to get there, and then also bringing in statistics and probability, which we'll do a little bit of, and other stuff. So it's enough of a challenge where if you're not being careful and you're overconfident, you can go down the wrong road. Anyway, we will cover derivatives next week, and then we will jump into some complicated problems that kind of sum up everything we've done this entire week. Hope you guys have a good weekend. Work very hard. If you're not working on this class, work on your other classes. Get ahead. Things are coming up. Exams will happen soon. Take care.